So here we're going to go to the unit 2. So write unit 2, lesson 5. And here, unsaturated hydrocarbons. So first, what are hydrocarbons? Hydrocarbons. The hydrocarbons are substances that mainly made of carbon and hydrogen. Hydrocarbons are molecules mainly made of carbons and hydrogen. What hydrocarbons we are going to study and what hydrocarbons exist? So we have the list. Hydrocarbons. We have alkanes. We have aromatics. We have alkenes. And we have alkynes. So this is the hydrocarbons that we are going to study. We are going to start by alkanes. So big 2, alkanes. First, to understand alkanes, we have to understand the carbon, because the hydrocarbons are made of carbon and hydrogen. And the carbon has a sweet property that the carbon can do the sp3 hybridization that allow the carbon to make 4 equivalent boundings. That's what we're going to say, that the carbon has 4 legs. So each leg has to bound to another atom. For example, with hydrocarbons, usually we have hydrogen and carbon. So, for example, for this carbon here, to be happy, it will be bound to some hydrogens. Yeah, and this property, it is very important for the carbon. Now, what if I have 2 carbons? If I have 2 carbons, so what the carbons will do? They will bound one to each other like that, and each one we're going to look for complete the other legs. So because there are lots of hydrogen, they will take hydrogen in each place. Hydrogen. And how many hydrogens I need in this case? I need 6. 1, 2, 3, 4, 5, 6. If I have 3 carbons, etc. So the alkenes have names, especially the first 10 alkanes. We are going to look at them. This is the first 10 alkenes. If I have only 1 carbon, how many hydrogens I need? I need 4. We saw it. 1 carbon, I need 4 legs, so I need 4 hydrogens. That's what we call it a methane. Now, if I have 2 carbons, I need 2 hydrogens, 6 hydrogens. We call it ethane. If I have 3 carbons, it is easy to know how many hydrogens I need. Put the carbons bound one to each other and then complete the legs, because each one has to have 4 legs. For example, this one has 4 legs. 1, 2, 3, 4. This one has 4 legs. 1, 2, 3, 4. And each one. Complete the legs, that every carbon has 4 legs, and you put the hydrogens and count the hydrogens. And it will give you how many hydrogens you need for each one. So for this one, we need 8 carbons, and we call it propane. So I have methane, ethane, propane. For 4 carbons, butane. For 5 carbons, pentane. For 6 carbons, hexane. For 7 carbons, heptane. For 8 carbons, octane. For 9 carbons, nonane. For 10 carbons, decane. You have to memorize this table here up to 10. Do we have more than 10? Of course we have more than 10 carbons. Here we have the table for the 10 first. But we can have a carbon with an alkyne with, for example, 100. 100 carbon. C 100, H for example 202. For 100 carbon we need 200 O2. There is a rule. If I have n carbons, the number of carbons is n, so we have a formula. The hydrogens that I need is 2 times n plus 2. So if I have 100 carbons, I put 2 times 100, it will be 200, plus 2, it will be 202. If I have, for example, 9 carbons, 9 times 2, 18, plus 2, 20. So it will be H20. This is what we have here. So this formula, it is for alkane. If we know how many carbons I have, I can know how many hydrogens I need, that the carbon will be happy. Okay, now we're going to speak a little bit about the properties of the properties of alkanes. If you have a molecule, start always by looking if it is polar or not, because the polarity will give us a lot of information. Alkanes are not polar. Alkanes are non-polar. Why they are non-polar? Yeah, we saw how we found is the molecule is polar or not. Now we're going to see why. For example, I'm going to take the ethane. The ethane has 2 carbons, C2, H8, H6. H6. So if I show the boundings for this molecule, I have carbon linked to a carbon. This carbon here links to hydrogens here, and we can use what we studied, what we learned in Unit 1. How I'm going to know this molecule is polar or not? First, I have to see if I have dipoles. I go, for example, for this bounding. Carbon with the hydrogen. Is the carbon with the hydrogen is polar or not? I'm going to check it. I have hydrogen bounded to the carbon. How we check it? First, we go to the electronegativity. What is the electronegativity of hydrogen? 2.2. What is the electronegativity of the carbon? 2.5. What is the delta electronegativity? The difference of electronegativity, it will be 2.5 minus 2.2. It gives me 0.3. And recall what we said, for the molecule to be polar, we have a rule. The difference of electronegativity must be greater than, I'm going to write it here, the rule. Negativity must be greater than 0.4 to be polar. But this one, it is 0.3. So it is less than 0.4. So what does this mean? This bounding here is no polar. So this bounding hydrogen carbon is no polar. Okay, by the proof that we said. So this hydrogen carbon is not polar. This hydrogen carbon is not polar. This hydrogen carbon is not polar. All the hydrogen carbons are not polar. So what is remaining? The one that is remaining. So I'm going to take this. Going to take them all. All the hydrogen carbons are not polar. The only one that we have to check, it is carbon-carbon. But carbon-carbon is non-polar. Why? Because the it is the same atom. The electronegativity for the carbon 2.5. If I have the difference of electronegativity, it will give me 0. This one, it is perfect non-polar. Perfect. There is no difference. Perfect non-polar. So, for example, though, for ethane, there is no bounding that is polar. If there is no dipole, so the molecule is non-polar. So, here we proved that alkane are non-polar. What we can deduce of that, what conclusion we are going to do? Intermolecular forces. Intermolecular forces. What intermolecular forces are in non-polar? London forces. London or dispersive forces. London dispersive. Sometimes we call it dispersive. London dispersive forces. And we said London forces are the weakest. London forces are the weakest. The weakest. So what we can conclude, what we can predict. So prediction, we can predict the boiling and melting temperatures, the boiling and the melting temperatures of an alkane are very low, compared. So I'm going to erase here, compared to a molecule, to a polar molecule with the same size. This is the prediction, and we know that it is because we saw it in the unit 1, compared to a polar molecule with the same size, Why we say with the same size? Because there are a rule about the same size. We have a rule about London forces. What is the rule? The rule of London forces. London forces became stronger and stronger with the rise of the size of the molecule. In fact, the number of protons of the molecule. More protons the molecule has, stronger the force is. I'm going to write it here. More protons the molecule has, stronger the force, the London forces. Stronger the London forces. Or the atom also, or the electrons. More electrons it has, more. Okay. So I'm going to erase now. Okay. So we know the properties. We know that the melting point and the boiling point must be low. Okay. So what we find in the practice, CH4 in reality is a gas. Why it is a gas? Again, it is small molecule. London forces are small, so it is a gas. But where we found the methane, so we found the methane, and it is the largest percentage of natural gas. First point. Second point, it is used to make methyl alcohol, acetylene, and ammonia. What about ethane? Also, it is gas. Why? Because the molecule is too small, only 2 carbons. So it is too small. We don't count the hydrogen. Hydrogen it is too small to count for. For example, I have CH4. Look, for example, I have CH4. How many protons I have in the carbon? I have 12. How many I have in hydrogen? Only 1. So even with the 4 carbons here, it adds only 4 protons. It is the third. That's why the number of carbons that That's count, not the number of hydrogens, because it is the number of protons it is carried by the carbon, not by the hydrogen. That's why, for example, I see here I have only 2 carbons. Even if I have 6 hydrogens, let's count for nothing. 6 protons compared to 24 protons. So ethane, it is also gas, and it is found in natural gas. Okay, so to go to the for the size of the molecule, it is the number of protons, and the one that holds most protons, it is the carbon. So propane also, it is gas, because 2 carbons are not too big, and it is the barbecue that help us to make barbecue. We found it in gas, fuel, barbecue, in barbecue. Butane. Butane also, it is gas. Gas with S, not Z. Z in French, but not in gas. And we find it where? We use it in lighters. What about pentane? Pentane, it is liquid. Why liquid? Because pentane, if I see pentane, I have 5 carbons and 12 hydrogens. Now, the number of protons, it is appreciable, because the carbon has 12 times 5, it gives me 60, plus the 12 protons of the hydrogen, it is 72. You see, the hydrogen, it contributes, but little, 12 regarding 60. So, the number of protons, it is a little bit appreciable. That's why it is liquid in normal temperature. But rapidly, if we raise the temperature, it will be gas. That's why it is dangerous, pentane. We use it where? High-grade gasoline. That's why it is very inflammable. Why? Because it is liquid, but small rise of temperature, and he becomes gas again, and he can do harm. Gasoline. What about hexane? Also, it is liquid. Now, all of the remaining are liquid. And hexane, we find it in naphtha. In naphtha. What about heptane? Also liquid. Gasoline. We found it in the gasoline. Octane, liquid. Also, we found it in gasoline. Gasoline. The nonane, also it is liquid, but this one we found it in fuel. And the decane, liquid, fuel, etc. Do we have more than 10 alkanes? Of course, we can have 100. For example, I can have C100, H202. If I have 100 carbons, how I can find the number of hydrogens? There is a rule. There is a rule. If I have, say, the number of carbons is n, if I have n carbons, so the number of hydrogens, it is 2 times n plus 2. This is the rule. For example, here I have 100, so it will be 2 times 100 plus 2. It gives me 202. If I apply it, for example, for this one here, for nonane, if I have the number of carbons, it is 9. So the number of hydrogens, I could put 9 times 2 plus 2. It gives me 9 plus times 2, it is 18 plus 2 to 20. This is what I have here. Okay, so you can, this is, so I'm going to stop here. This is the introduction of hydrocarbons. I don't want the video to be more than that. Okay, bye.